Thank you very much to the organizers for all of your work doing this conference. So I'm just tremendously thrilled that you guys have put this together, and you've got such a great batch of people here attending and running these projects and participating. So I couldn't be happier. And I'm also very honored and pleased to be able to lead a group again with Bianca Varai. And so the way we're going to structure our presentation here is that we've divided it in half. And in the first half, I'm going to talk about the paper that we wrote that came out of the Win1 project. So this is joint work with our group from last time, which was Helen Grunman, Jennifer Johnson-Long, Adriana Salerno, Bianca Varai, and Erica Wittenborn. And then in the second half, Bianca is going to talk about the work that we continued in this direction. Bianca actually came and did an internship at Microsoft Research the summer after the last Win. And we have continued on this direction of collaboration and proved some new results. And that will lead us to be able to explain to you what our project is for our group this time. So to start with, what I'd like to do is to give some background. I mean, this title is kind of horrendous, right? You're not expected to be able to parse this very well to begin with. So this is numerical evidence for the Bruinier-Yang conjecture in comparison with denominators of Igusa class polynomials. So basically what I'm going to do is I'm going to start with the Igusa class polynomials. I'm going to tell you what they are and why we're motivated to study them. And then I'm going to tell you what the Bruinier-Yang conjecture was and tell you a little bit how we studied it and how it's related to the work that Bianca and I did and what our project is. Okay, so I always like to start with a little bit of motivation for this topic. So at Microsoft Research, I work a lot on cryptography, and I just have to get an idea. I mean, how many of you already know all about like elliptic curve cryptography? Okay, so something about it. So if I voted, I could do like Melanie did, and I could have you vote. So if you had to join the elliptic curve frisbee team or the hyperelliptic curve frisbee team, which would you join? So what I'd like to talk about is related to a generalization of elliptic curve cryptography. So the motivation was for constructing actually genus 2 curves for cryptography. We've heard a little bit about in some of the other presentations this week about people that are studying abelian surfaces. So the abelian surface, which is the interesting topic in this talk, is the Jacobian variety of a genus 2 curve. So a hyperelliptic curve of genus 2. The Jacobian can be used in cryptography in much the same way that an elliptic curve, the group of points on an elliptic curve, can be used in cryptography. So cryptographic systems are often based on hard mathematical problems, and one of the standard ones is called a discrete logarithm problem. So if you have a very large cyclic group, let's say, and you have a generator for that group, and then you take any other element of the group, how do you know which power of the generator it is, or which multiple of the generator, depending on whether your group is written additively or multiplicatively? So that's a discrete logarithm problem, and many cryptographic systems such as key exchange, encryption, or authentication through digital signatures are based on systems built on these groups. So the elliptic curve group has been used, and the group operations have been optimized, but there's a lot of interesting questions in number theory that come up when you want to use an elliptic curve in cryptography. So one of the main ones that I've worked on that I like to talk about is how do you generate an elliptic curve with a certain number of points. So you know that the number of points is going to be in the Hasse interval, and so whatever your prime is, p, it's going to be roughly p plus 1 plus or minus square root of p. But let's say you want a group order which is prime, which is what you need for cryptography. Then how do you pick a prime in that interval, and then how do you generate an elliptic curve with that order? And so the best known methods are these basically called CM elliptic curve methods, where you use the theory of complex multiplication and basically like explicit class field theory to generate the maximal abelian unramified extension of the quadratic imaginary field K, which appears. And so what I'm going to be talking about here is the analog of that CM theory now for genus 2. So why would we want to do genus 2 instead of genus 1? So I believe Alice wrote on the board what the group order is, roughly. So like I said, the group order for the group of points on an elliptic curve is roughly p. It's p plus 1 plus or minus square root of p. But for the genus 2 curve, the group order for the Jacobian is roughly p squared. So the advantage is you can have a smaller field and still have a bigger group. So if you want a group of size 256 bits, you could have your p be 128 bits instead of 256 bits as it is for an elliptic curve. And this actually makes a difference for implementation. So that's kind of the motivation is that your p can be smaller. And actually there's a lot of work that goes on with trying to make these group operations competitive with elliptic curve, and they actually are very competitive. So now we're left with the question, the analog of the question for elliptic curves. How do we generate a genus 2 curve with a certain number of points on the Jacobian? So the problem is that point counting algorithms are even worse for hyperelliptic curves than they are for genus 1 curves. So genus 1 curves, there's polynomial time algorithms due to Scope and lots of improvements using the AGM method and p-adic methods, which are really fast. So you can almost solve the elliptic curve problem by just picking random curves and then taking these super fast point counting algorithms and just counting the number of points. This is still not true for genus 2 curves. For a large characteristic, there are very special cases where you fix the real quadratic field where you can count the number of points on genus 2 curve of cryptographic size. One single curve, like within a reasonable amount of time, meaning like a couple of weeks. So it's not the kind of thing, it's far from being the state of the art that we can actually just pick random curves, count the number of points, and decide whether to keep them. That's not, we're not there yet. So instead, we're stuck still with these methods of actually constructing them to have the certain number of points that we want. So given, basically, here's the problem. Given a desired number of points, like Alice wrote this h of 1, so it's the characteristic polynomial, meaning the numerator of the zeta function, evaluated at 1. Given a value for that, how do you construct the curve? Well, what I'd like to explain first is that this determines, this quartic polynomial determines a quartic CM number field. I'm always going to assume we're in the ordinary case here, so I want to avoid dealing with supersingular abelian varieties. And starting from this characteristic polynomial Frobenius, we're going to try to construct a genus 2 curve. So what's the number of points going to be? Well, the zeta function of a genus 2 curve is determined by two pieces of information, n1 and n2, which is the number of points on the curve over the base field and over the quadratic extension. And if you label these n1 and n2, the number of points on the Jacobian can be written explicitly in this form. So it's n1 squared plus n2 over 2 minus q. And then if you set S1 and S2 equal to these values, then this is the quartic polynomial. So I just wrote this explicitly so that you can see it's easy to go back and forth here, and that this is not a complicated computation. This is start with your number of points that you want, here's the quartic polynomial, and vice versa. So, but what this does is that means once you say what your zeta function is that you want, that determines a quartic CM field determined by this polynomial. So this is now, for the rest of the talk, unfortunately, curves are going to disappear, and the only thing left is going to be this quartic CM field. So just think of it as the analog of the imaginary quadratic field that you work with in CM theory for elliptic curves. Okay, so we also are going to assume that it's a primitive CM field. This avoids the problem of getting abelian surfaces, which are products that are decomposable. They're not simple. So a curve C over the complex numbers is, we say it has CM by OK, if OK embeds in the endomorphism ring of the Jacobian. So if you have heard of this terminology before, there's a bit of ambiguity because some people will say a curve has CM by K if some order in OK embeds in the endomorphism ring. So in this talk, I'm talking about looking at the maximal order OK embedding in the endomorphism ring, but you can certainly consider the more general case. So the Siegel moduli space parameterizes abelian surfaces with principal polarization. So it actually has a very nice concrete description over C, which is basically in terms of period matrices. So what you can do is you can think of, actually when I gave my talk at Win 1, I explained this theory kind of in detail, which I don't have time to do today, but you can think of just like the moduli space for elliptic curves that came up in in Ling's talk, you can look at parameterizing the abelian surfaces by taking the Siegel moduli space. A polarization can be thought of as a Hermitian form on a complex abelian surface. So for this description, think of a complex abelian variety as being like C to the G modulo some lattice, just like an elliptic curve, but in higher dimensions. So just think of this as, basically C2 mod a lattice. And if you write this lattice in this way, where tau is going to be what we're going to call the period matrix, so this is like a 2x4 representation here. This is the identity, and this is a 2x2 matrix. This tells you essentially what the Hermitian form is on this complex abelian surface. So this is called the period matrix, and this collection of 2x2 matrices is now going to be what we call the Siegel moduli space. So Igusa gave 3 modular functions on this moduli space. We call them the absolute Igusa invariants. There's actually not just one choice that you can make. There are many choices that you can make for these functions. But there's a particular choice that people have been using quite a bit for computation over the last 10 years. So we call those the Igusa invariants. And they generate the function field of this moduli space. And I'm going to show you what the modular forms are because they're kind of important for our computations. So these are Siegel modular forms on the Siegel moduli space. And what you should notice is that they're quotients of, these are modular forms of the same weight in the denominator and the numerator. So these are Siegel modular functions. But look at all the numerators. All the numerators are the same. They have the same modular function in the numerator, or it's denominator, sorry, denominator. And so the point is that we want to study, I'll tell you why we want to study these functions, but these functions are actually very computationally intensive to compute. So it actually matters this way, the algorithms that you use to compute these things actually matter. Yes? Well, no, this is a cusp form of weight 12, and it's to the 5th power, and this is a cusp form of weight 10, and it's to the 6th power. Yes, and these are the cusp forms, and these psi 6, psi 4, these are the Eisenstein series, so they're the analog of the usual Eisenstein series, and these are the cusp forms, which can each be written as linear combinations of these Eisenstein series. Okay, so what I'm explaining now is the analog of the Hilbert class polynomial. So the Hilbert class polynomial takes it runs over all the isomorphism classes of elliptic curves with Cm by a certain imaginary quadratic field K. And then it takes their J invariants and it forms this polynomial x minus J of tau I, where tau I varies. Now here's the analog for genus 2. You run through the moduli space isomorphism classes of abelian surfaces with Cm by OK, and you look at now the Igusa invariants. So instead of the value of the J function, you've got the value of these modular functions, these Igusa modular functions. So this is just by kind of the standard CM theory, essentially what you've done is you've constructed a polynomial where you ran through all of its conjugates over Q. So clearly, this polynomial has coefficients in Q, but the problem is it does not have coefficients in Z. So the coefficients of these polynomials, one for each of the 3 invariants, are what we want to compute. So just to relate back to our original problem of having to construct a curve with a certain number of points, we want to compute these functions so that what we can do is mod p, we can take a root of them, we'll know that those roots are the invariants of this curve, and we can work backwards to write down what the curve is, having constructed these polynomials. And that's exactly how the elliptic curve method works as well. It's just that this is a little bit more complicated. So the worst thing about this situation, this problem, is that there are denominators in these polynomials. The coefficients are not integral. And the problem is that makes it so that you don't know how much computation you have to do in order to succeed. So you don't, in a sense, you could say you don't have an algorithm. Because you can go ahead and compute these egomodular forms and just compute and compute, and then you get a result. And first of all, it may not be recognizable, and you don't know whether you made a mistake or whether you just didn't have enough precision. And second of all, even if you do recognize something and you think it's right, you haven't proved that it's right because you don't know whether you did enough computation or not. So the whole problem in this area is really, the really big problem here is understanding these denominators. So just in the interest of time, I'm going to skip over a little bit of the history of working on different algorithms in this area. The complex analytic method actually goes back to Spalek, a student of Fry, and I first implemented this about 10 years ago at Microsoft Research with Henry Cohen, and I worked quite a bit on this with Kirsten Eisentrager on what's called a Chinese remainder theorem approach to this problem. So I'll just go right to the example. I'd like to give an example to give you guys an idea of what type of object are we computing here. So here's a quartic CM field K, and it's actually non-normal, and it has class number 4. So it's generated by this element here, written I times square root of 25 plus 2 root 133, and this is the real quadratic subfield. And the discriminant is 3 times 31 times 133 squared. I wrote down what the reflex field of this quartic CM field is. This may be just kind of interest for our group because we're doing a lot of computations with the reflex field, but I haven't defined the reflex field in this talk, so you can just kind of ignore this for the time being. Okay, so this is just 2 of the coefficients of the first class polynomial. So what happens is, the way I've written this, I've written it as monic, and the denominator is here. This is the denominator. So if you can imagine, like more than 10 years ago when I was first computing these things, we would literally compute for weeks and weeks and weeks, and usually it wouldn't succeed, and then we'd start it over again and then compute again. And finally, you know, we would get something recognizable and it looked like this. And so then imagine my surprise when we factored this, and this is what we found. Okay, so super small prime factors. And so just this is a kind of a historical note here, because these were computed a long time ago, but it was computed with 1,000 digits of precision in about 8 hours each on a Pentium 4. So at that time, I really was surprised by how small these primes were, and started thinking about the connections with Gros-Saguier. And even though it was not at all obvious how Gros-Saguier was related to this problem, I started checking it out, and it looked like all the primes that appeared were of the form they divided the discriminant of the field minus the square. And in fact, one thing that really bothered me always was that originally when I stated this also, I even wrote the relative discriminant minus the square. And the relative discriminant in this case is 3 times 31. I had it written there. You see? This is the discriminant of the real quadratic field, and the relative discriminant is the discriminant of the top part, the norm of the discriminant of the top quadratic extension. And 3 times 31 is 93, last time I checked. And so the reason I use this example is that this was the first example that I found that had a prime that was bigger than 93. And that's actually a little bit relevant to some things our group has been discussing as well. But like 93 minus 4 is 89, et cetera, et cetera. So in all the previous examples, it was even the case that the relative discriminant minus the square, all the primes divided. Go ahead.
That's a 12th power also, yeah?
Yeah, now that is also because of that high power of the modular forms in the denominator.
Okay, so
that's why.
Then
so
you don't have such a big number because
yes.
You know it's a 12th power.
And now, in fact, we compute with slightly better invariants, which have like a 4th power instead of a 6th power, or things like that. But still, so what you should, that's a very good point. What you should think of these exponents, instead of thinking of them as, whenever you see a 12, you should think of it as a 2. Like divide by 6, because this is for the first invariant, and it was to the 6th power. But you can still see the 7 is to a high power. It's basically 7 to the 8th. Okay, so in order to connect to the kind of methods that we actually use to address this question of how do we understand these denominators, the main tool, the main thing that I need to explain is what are these denominators geometrically. So there's this modular form chi10, and it's in the bottom of all of these modular functions. And what is this? Well, here's a definition of it in terms of what are called the even theta characteristics. Now, I haven't written out what the theta series is, but anybody that works with modular forms, even if you've only worked with classical theta series, the definition for higher dimensions is very analogous. So it's a Siegel modular form of level 1 and weight 10 on the moduli space. But the important part is that, and this is very classical, this goes back to like Riemann or something in the complex space. The divisor of this modular form is the locus of abelian surfaces, which are products of elliptic curves with a product polarization. So if you think of the period matrix, this is over C. The period matrix is like tau 1, tau 2, 0, 0. So it's diagonal, and the polarization is decomposed. And that is not the Jacobian of a genus 2 curve. That is a product of elliptic curves, which is an abelian surface, but Jacobians have an irreducible theta divisor that comes from the embedding of C into its symmetric product. And so when you have an abelian variety that decomposes in this way, it's not the Jacobian of a curve. And so what you're looking at here, what's happening is, when a prime appears in this denominator, it's because you started out with having a genus 2 curve with a Jacobian over C, with CM, so it's defined over some number field. But then modulo P, the variety decomposes into a product of elliptic curves. So you're not getting the Jacobian anymore, and instead you're getting this kind of product of elliptic curves. So the statement is that if P appears in these denominators, then the curve, when you take it mod P, decomposes into a product of two supersingular elliptic curves crossing transversely at their origin. And so I haven't really explained yet why I'm saying supersingular. I'll explain that in just a second. But so just for your amusement, I will note that we call these evil primes. So up until this point, starting at about this point, I'm going to describe some work that I did for a number of years with Eyal Goren at McGill University. And so we studied this problem, and we actually wrote a paper with evil primes in the title of the paper. Okay, so the bound that we got with our methods in joint work with Eyal Goren was, if you write your quartic CM number field this way, where D is some positive integer, square-free integer defining the real quadratic subfield, and R is some totally negative element of this real quadratic field, and then you join the square root of that, so you get an imaginary quadratic extension on the top. If P is an evil prime, then P has to be kind of small compared to the size of the number field. So if you recall, my conjecture was that it had to be kind of bounded by the discriminant. And this is actually not quite the discriminant, but it's very close. The discriminant would be D squared times trace of R squared minus another quantity squared, which is potentially slightly smaller than this. But morally, this is a bound that says that roughly the primes are bounded by the discriminant. Not quite. So it's a little bit unsatisfactory. Plus, we did some follow-up work, which actually only appeared this past year, 2011, which bounded the power to which these primes can appear. And those two pieces of work together actually make it so that we do have an algorithm for computing these class polynomials and Igusa class polynomials and computing curves. But unfortunately, the bounds were not very tight. This is just a bound that says the rough size of the prime. The powers were tremendous overestimates, which makes a huge difference when your powers, it's not just your prime is too big, but your power is way too big. And so the problem is that for computational purposes, those bounds are just not tight enough. So that brings me to the kind of second part of the talk, which is to explain about Bruinier and Yang's work, which is related to what Bianca's going to talk about and what our project is. So I guess what I want to say about Bruinier and Yang is that they came up with a conjectural formula for these denominators which describes them exactly, like which primes appear to which power. And that's a big improvement from a computational point of view. Okay, so I think one more thing that I need to say before that is to talk about the strategy for how we proved this, this theorem on this bound, because this is also what we study in more detail now. So if P is an evil prime, and this is, I'm going to explain why I said that the decomposition would have to be a product of supersingular elliptic curves as well. So if P is an evil prime for K, then it means, like I said, that there's a curve that has its Jacobian variety, is an abelian surface with Cm by K, but which decomposes mod P into a product of elliptic curves. So think about that. It had an endomorphism ring when it was living in characteristic 0. It had Cm, so it had OK basically as its endomorphism ring. Now you decomposed it mod P, and it became, and this is a rank 4 Z module. Mod P, it became a product of elliptic curves. And so what's the endomorphism ring of a product of elliptic curves? Well, you can show that if E1 and E2 were not supersingular and isogynous, then you would not be able to kind of fit this endomorphism ring into this one for primitive quartic CM fields. So that's what gives you the conclusion that these two things must be supersingular. And then, so what is the endomorphism ring of this product? Well, it's of this form. So it's matrices of this form, like endomorphisms of the first one, endomorphisms of the second one, and homomorphisms between them. But now, since these are supersingular elliptic curves, these are rank 4, these are maximal orders in quaternion algebras. So this thing here, this whole right-hand side, this has rank 16. So now we have this kind of what looks like a complicated problem, which is to study how can you possibly have these embeddings of this commutative rank 4 thing into this non-commutative rank 16 thing. And so this is what Eyal Goren and I called the embedding problem. And we actually proved an equivalence of this with solutions to the embedding problem with, this is only one direction, but with P being an evil prime. So we've actually proved an equivalence. The other thing that I didn't state is that a polarization on an abelian variety induces an involution on the endomorphism ring. And so that's what we usually call the Rosati involution. And the extra condition that's important here is that the product polarization induces a Rosati involution of a particular form of this kind. And when OK is embedded in here, it has to act as complex conjugation on OK, which is a condition that we use very strongly in studying the solutions. OK, so I have only 10 minutes, and I need to explain the Bruinier-Yang formula and explain the computations that we did to study it. Okay, so basically what I was talking about up till now was on the Siegel moduli space. These are abelian surfaces with principal polarization. And we looked at Cm points, which are abelian surfaces with Cm by K. What Bruinier and Yang study is actually on the Hilbert moduli space, which just means these are the abelian surfaces with polarizations, but they've already fixed an action of a real quadratic subfield, which of course we're interested in this anyway. We have a real quadratic subfield in our quartic field. So they were studying certain divisors on this Hilbert moduli space, in particular something called the Hirzebruch-Zagier divisors, T sub deltas. And the important thing to note is how it's related to our problem, that chi10 can actually be written as 2 times this Humbert surface, where this Humbert surface can be written as a sum of these Hirzebruch-Zagier divisors. So don't worry, I haven't defined any of these things. So I'm just going to kind of skip over the definitions. But what you should think of is that they were interested in certain intersection theory on the Hilbert moduli space, but it's very related to basically the intersection theory that we want to study on the Siegel moduli space. So here's their formula for this intersection number. And it was a conjecture that appeared in their paper in Invenciones in around 2006. And I'm going to have to tell you what all of this kind of complicated notation is, but I'm going to try to do it quickly. And the point you should think of is that these are just things that can be computed fairly easily in terms of the field K. So in contrast to trying to compute values of Siegel modular forms, which is a very huge and taxing computation, these are relatively easy computations directly from the invariance of the CM field. So here they write L is the real quadratic subfield. Its discriminant has to be 1 mod 4 and prime. The reflex field is, well, I haven't defined reflex field, so I won't talk too much about it. But the norm of the discriminant of the reflex field, it has to also be, we denote it d tilde, it also has to be 1 mod 4 and a prime. So what this means, those two things together, this means that they're only looking at CM fields K that have discriminant of the form d squared d tilde, where d and d tilde are 1 mod 4 and prime. So it's actually extremely restrictive. This is only kind of a special class of CM fields that they're covering with this formula. And here this is like, for example, this T was written on the previous slide. This is an element of like the inverse discriminant in this field L star. And so then they have, oh sorry, this isn't supposed to be in the subscript. This is supposed to be an L inverse. So then they have to compute like the order at a certain prime of this element. Here they have to compute the, oh, my group is going to think this is really funny. I try to do frac A's here in tech, and they disappeared. I'm so sorry. That's so funny because we've been having trouble drawing frac A's on the board. This is supposed to be a frac A of this quantity, which means the number of ideals of that norm. So there's supposed to be a frac A here and a frac A here. I can't even do it in tech. Okay. Okay, so this is the Bruinier-Yang formula, and as you can see, it's complicated, but it's computable, very computable given a CM field. So the consequences of it are that it produces a bound, a better bound for the size of the evil prime. If the conjecture is true, then the bound would be d tilde over 4 instead of the rough bound that we had from the work with Eyal Gordon, which was d squared times d tilde. So that's better, that's good. But even more than that, it's like tells exactly which primes appear and to what power. So it's really good. And Yang actually proved this conjecture for d1 or d and d tilde primes congruent to 1 mod 4 using a very detailed study of the embedding problem and a few other major tools from number theory. So there was this proof. Now this was prior to the last WIN conference. So starting in our project in the last WIN conference, what we decided to do is to look at fields basically which are not covered by Yang's proof, try to understand whether this conjecture extends, and to study whether the, what the actual number of, what the actual powers of primes that appear are. So I would say, like, if I were to summarize what the contributions of our WIN paper were, we studied these numerical values for Bruinier-Yang. We studied 3 things that we computed. The numerical values for Bruinier-Yang, the denominators of the Igusa class polynomials, and the number of solutions to the embedding problem. So this embedding problem, as you could kind of see, is pretty complicated. So one of the main contributions of the WIN project was an algorithm which produced the set of solutions to an embedding problem. So in particular, counted the number of solutions to the embedding problem. Another contribution of the paper, the WIN-1 paper, was that of course, we both confirmed the Bruinier-Yang conjecture in cases where it was known, but we showed that it does not extend beyond the conditions that they had imposed for their conjecture. So we found, you wouldn't call them counterexamples, but you would say that if you tried to use the Bruinier-Yang conjecture more generally, you would see that it's not true. So that's what we kind of established with our project, which was very useful. Because people actually use this in computation to compute these denominators. So it's important to know if it's not true, right? So let me show you the data. So these are what we did was we took all the von Wamelen examples. So von Wamelen wrote a paper in Mathematics of Computation which gives all the CM genus 2 curves that are defined over Q. And these are all the CM fields. There's actually 13 fields, and some of them have class number 2, so there's 19 curves. And in each of these cases, we've written d tilde here. You can kind of see what d is from the discriminants here. And then what we did was we looked at the denominators of the Igusa class polynomials in this column. This is the Bruinier-Yang formula, and this is the number of embeddings computed with the algorithm to compute the number of embeddings. So, and there's, in case you were wondering why it didn't look like there were 13 things on this slide, this is the rest of them. So in the cases that have a single star, these are places where the conjecture was proved, and a double star means that the conjecture was not even really stated for those cases. It's not covered. So actually, Bianca had some larger slides, which I decided to use because they're a little easier to see. So here you can see d tildes which satisfy the conditions of the conjecture. So these are 1 mod 4 and prime, and the d's are 1 mod 4 and prime. So what you see is that if you look at the denominators of the Igusa class polynomials, you look at Bruinier-Yang, and then you look at counting our embeddings, these all match up. So what this means is, like for the prime 5, for example, here this means there's 2 embeddings. And Bruinier-Yang was 5 squared, and the denominator was 5 squared here. And so actually the only place where you see a difference is that for our embeddings, what's happening is this embedding is appearing with multiplicity. But our initial project didn't count multiplicity, so we weren't seeing this 4 showing up, and that's because there was only 1 embedding, but it had multiplicity. So here's cases which are not covered by the conjecture. So these, you see there's a square power here in this d tilde. Yet if you look at the data, everything still worked out fine. So we had matching up basically the Igusa, the Bruinier-Yang, and the embeddings, they all matched up. So those cases look good even though they're not covered by the conjecture or the proof. Okay, so now we start getting to the disaster zone. See these d tildes? They are divisible by 2. And if you come over here and you look at Bruinier-Yang, you see these disastrous numbers, fractional powers. Not good. Here's another one, so even negative fractional powers. Okay, so these things are clearly anomalies. There's something wrong, right? And actually, Bianca figured out that one way, one thing is that Bruinier-Yang is actually kind of missing a congruence condition that is necessary in general when you don't have their conditions. So with that, you were able to make some of these problems go away. But I'll just point out a couple of, I'm not sure if I'm going. Oh, darn. Okay. So I'll just point out 2 other things that were anomalies that we found. Oh, that's unfortunate. I'm looking for the 23 example. Okay, sorry, I'm going to go back up to my other slides. Here. So the last thing that you can see here, here's another anomaly where it's not a question of, it's not just a problem of fractional powers, but in the number of embeddings, we have 23 to the 4. We have 223 squareds here, so these 2 columns match, but does not match Bruinier-Yang in the middle. So this was a particularly puzzling example. So I'm out of time, so I'm not going to say any more about this. Bianca's going to talk more about it. But what she's going to say is basically explaining an arithmetic intersection formula that we proved, which is true more generally than Bruinier-Yang. And our project is relating the Bruinier-Yang conjecture to our formula and showing that they're actually the same in the cases that are both covered by those examples. So